Okay, let me just touch on a couple of things we talked about last week. Remember the footings, that those are the feet, that's what the building is resting on. We see them as hidden lines when we look at foundation plans. And those footings have to rest on undisturbed earth below the frost line. There's rebar inside that concrete. And the size of the footing is determined by two things: the weight of the building and the type of the soil, right? How much weight we have to support and what we're trying to support that weight on. Right, we had frost line depth before. Remember the footings have to be at least 12 inches below the frost line. Frost line is 42 inches in Chicago, right? You see on the map there, it's going to be a lot more if you're in Duluth, Minnesota, and a lot less if you're in the south of Florida or Texas or someplace else. So I would say if you're building residential site, you probably know based on the general location you're building and what the soil conditions are. If you're building a commercial building, you're generally going to do some kind of soil testing to know exactly the conditions of the soil, and that soil testing results will be given to the structural engineer or the civil engineer who's ever doing the foundation design to make sure that they design the foundations or footings or columns or pilings accordingly. Right, so footings have to extend 12 inches below previously undisturbed soil and be 12 inches below the frost line. The width of the footings depends on the nature of the soil. It says here minimum width of 12 inches. Typically the footing is at least twice as wide as the foundation wall. And this LBV load bearing value of the soil, I believe it's in pounds per square, here it is, in pounds per square foot. So again, depending on the nature of the soil that you're building on, you may have to widen the footings. Certainly if you're building a commercial structure that weighs a lot more, you'll be doing different types of foundations than just a simple footing on soil. And we'll see that here in a little bit. Right, again, cutaway, a foundation wall, reinforcement, keyway that locks the two things together. Quite often the footing is poured separately from the foundation wall. Right, you see here a picture of a footing with the rebar coming out of the footing being ready to pour the foundation wall. Right. Again, we typically don't have columns in a residential building, but we'll have columns in a commercial building. And again, those columns have footings. The footing of the column is generally speaking going to be wider than the foundation footing because that column is carrying a heavier load. We looked at these before, so I'll just go through them quickly. If anyone has any questions, please shout them out or put them in the chat. Right, here are the hidden lines showing the footing and foundations in an elevation. Okay, so this is where we left off last week. So all the footing for a column is going to be wider and thicker due to the fact that that column is carrying a heavier load. It's going to be a concentrated load, so all the load on that column has to be distributed to the footing. If we have, a chimney or some other thing that has loads greater than typical, then that might require a thicker or larger footing than the rest of the building. We're going to come back to green building at the end of. So again, we talked about the footing. The foundation wall is the base. We're transferring weight from the structure to the footings. The foundation walls can be either poured concrete or concrete block. In both cases, we're going to be using rebar. And again, we're dealing in unit 10 here. And sorry, I should give you a page reference. We should be in unit 10. We're on page 172-ish. Right, in concrete construction, you quite often have expansion joints. Right, expansion is to allow materials expand when they're heated or warmed, and they contract when they're cool. So if you have a slab pushing up against a foundation wall, you're going to have an expansion joint. Right, as you walk down the sidewalk in front of your house, those lines you see every 5 feet or so, those are expansion joints. You obviously seen them your whole life. You may not have thought about why they're there, but they're there for the same reason, right? They're giving that concrete at the surface of the sidewalk some place to go when it expands due to an increase in temperature. Right, here is a foundation wall section. This is figure 10-6 on page 175. Again, you see the footing, an indication of the, where's my pointer? Boom. Indication of the top of the footing there, top of the footing elevation. So that's obviously would reference some point on the plan or on the site. Top of slab, this next line here is, it says T slab, so that would be top of slab. Top of the foundation wall and the finished floor elevation. Again, a picture, right, in plan and kind of a representational drawing of a foundation wall. Right, so you see the foundation wall, the footing, in this case, a basement slab. And in this case, there's also a drain tile, surrounded by gravel at the base of the footing. And you can kind of see what would be the soil that was excavated to allow that foundation to be poured. And then the undisturbed soil around it. So again, hopefully we've dug down deep enough so we've gotten to undisturbed soil. Again, another view of a foundation wall. In this case, this is showing what's called a monolithic slab. Monolithic slab is figure 10-12. So in this case, they would have been poured, this slab and footing would have been poured together. And then you see in this case, we have the foundation wall is concrete blocks, right, with rebar tied into the foundation wall. And remember, we were looking at the wall section for Delhi the other day. Right? We talked about Delhi being a single course of concrete blocks that was 17 feet tall. So this is how they do it, right? You have rebar coming out of the footing, and as you stack the blocks up, you're extending that rebar up, and then you're filling in or grouting the cores of the concrete block. I think in the case of Delhi, the reinforcement was 4 feet on center, So some of the cores are going to be filled with concrete or grout, and some of the cores were filled with insulation, if I remember the detail correctly, right? So that's what, if you're wondering what that wall of Delhi looks like, that was the north wall of the hardlines room, right? That's what it looks like as a picture, right? The slab and foundation might be slightly different, but again, that's how your, the rebar is what's allowing you to build that single course of concrete block, right? It was 17'4" from finished floor to the place where the bar joist was bearing, right? Something like that. Right, again, here's a foundation wall detail. In this case, we've embedded a rod into the top of the foundation wall where the sill plate is going to bolt into. Again, this would be a typical detail for residential construction. Right, we have waterproofing or dam-proofing, we have insulation, we have finished grade. We're sloping the grade away from the foundation wall to give the water a chance to drain away, and then we're building on top of it. Here's another way that we could build the foundation wall. ICF is insulated concrete forms. So those of you who have taken ARC 108 or 110, we talk about different wall types. ICF is one of the wall types we talk about, so we can use ICF as our forms for the foundation wall. So again, this is rigid board insulation. That rigid board is tied together. You see the rebar coming out of the footing. Pardon?
The styrofoam, what is it, like a moisture barrier type thing?
What's the point of that? Well, the point of it is the insulation. Typically in a, that was Alan in the classroom here asking a question. He was asking about the type of insulation that would be, it's typically going to be expanded, probably extruded polystyrene. On the systems that I'm aware of, sometimes these little black trusses will poke out the other side to give you a place to attach drywall or something else, whatever the finish is, because the below grade on the outside, you're okay with insulation, but inside you have to cover that insulation with something else, with drywall to provide fire resistance. But this is really to show that there are a couple of different, a number of different ways that we could build foundation walls, block or brick or poured in place concrete.
So quick question, that ICF would remain in place, it would not be removed once the concrete is set?
Yes, that is a good question, Nicole. Yes, the ICF remains in place. So this is different than a typical form, right? Typical formwork, you build the formwork, you put in the rebar, you pour the concrete, and then you take down or strike the forms when the concrete has set up a little bit. In this case, the insulation stays. But yeah, good question.
Thank you.
Right, remember, concrete reaches its ultimate strength in 28 days or so, right? You don't wait 28 days to strike the forms. You're going to strike the forms within a day or two. But let's say you're building a high-rise building or a parking garage, you're going to strike the forms and keep moving upward, but you're not going to drive cars into that parking garage until the concrete has reached its full strength. Right, a grade beam is that here spans from footing to footing. Here we're using it to span over weak spots in the soil, right? So we're going to span from footing to footing with a grade beam. And in this case, we're just digging a trench, putting the rebar in there, and then pouring the concrete. So it says earth provides the form for concrete. Let me see where it talks about grade beams. That's figure 10-8 on page 176. And again, here's a picture of a grade beam, right? You see there's no form work there. There's rebar, but no form work, right? So there's nothing to strike because you don't have a form, right? You have form work elsewhere, but not form work for the grade beam. Okay, so the things you're looking at there, footings and foundations would apply to residential and small commercial construction. If we are getting into larger structures, more stories, heavier weight, then we have to find some other means to hold up that building, right? Generally speaking, we're going to have to find a means to get down to bedrock. You saw that the LBV of soil might be something around 2,000 pounds per square foot. If you get down to bedrock, the LBV is 6 times as much, or 12,000-ish, right? So if you're building a larger, heavier commercial structure, generally speaking, you're going to have to get down to bedrock one way or another. So we're going to look at a couple of different ways that we get down to bedrock. So one way is with an auger cast pile. And I'm actually going to play a couple videos here that will show what that means. Right, there's just a paragraph on page 174 for an auger cast pile. Basically, an auger is like a giant screw. We're going to use this thing to drill a hole in the ground. We're going to pull the auger up. We're going to pump concrete into the hole, and then we're going to put some reinforcement into the hole. So that's an auger cast pile. And right, the image is a little fuzzy here, right? So we're going to drill to depth, right? Let's say our soil boring tells us that bedrock is down 14 feet, right? So we gotta drill an auger 14 feet deep to get down to bedrock. So we drill the hole. We're going to pump pressurized concrete into the hole, and then we insert the rebar. It says while concrete slurry is wet, right? So we have to make sure we don't dilly-dally and let the concrete harden before we got to stick the rebar in there. Right, another image of auger cast piles. Again, these are things that would be typical. Good evening, Pablo. We're in the middle of Unit 10 on foundations, so we're talking about auger cast piles on page 174. I've got some pictures in here that aren't in the textbook. So again, same thing. Drill a hole, pump it full of concrete, put rebar in. My predecessor who built this presentation gave us a lot of pictures here. Again, you're not going to see this in residential construction. No worries, Pablo. And I actually have a video here, so let me see if I can find my video and get it to work correctly. Okay. Ooh, that's not good at all. I'm not liking that. Okay. Let me try one more shot at that. And otherwise, let's try it over on this screen here. Sorry, folks, I'm in a new world here.
Continuous flight auger piling is a fast and economical piling method, ideally suited to wet or granular ground conditions, which otherwise would require the use of temporary casings to support the ground. Pile depths of up to 32 meters depth can be achieved using powerful crawler-mounted drill rigs. A CFA pile is constructed by rotating a full-length auger into the ground to the required depth. Auger diameters from 450 millimeters to 1200 millimeters are common. The auger has a hollow stem which is connected by a flexible hose to a concrete pump. The hose and stem are charged with concrete before drilling commences. Once the auger reaches the required depth, concrete pressure dislodges a temporary cap at the base of the hollow stem, and concrete is pumped under pressure into the ground while the auger is withdrawn, carrying the excavated soil upwards. Different designs of auger cleaner require the auger to either be stationary during extraction or to be slowly rotated in the same direction as used when drilling. Soil is flighted up the auger and is removed by an auger cleaner just above the ground surface. Once the tip of the auger returns to ground level, concrete pumping ceases. The accumulated soil is then cleared away from the pile. Then a prefabricated reinforcement cage is plunged into the pile while the concrete remains fluid. Special attention to the concrete mix design is required to maintain its workability and to ensure that the reinforcement cage can be inserted to the required depth. The pile concrete is allowed to set before nearby piles are constructed. Piling contractors. Think safe, work safe, home safe.
Okay, oops. Let me stop that and share my file again. Does that make sense, folks?
Yeah.
Good. Let me find where I was here. Right, we're looking for ways of getting down to bedrock. Sorry, this was in, you guys have to convert between SI units and English units. They talked about how many meters the auger length is. Right, again, this is figure 10-9. In the book, again, we might have multiple augers put together with a pile cap to form the base of a single column. That's what this particular detail is showing, right? So we'd have 4 auger cast piles in close proximity to each other with a pile cap that's going to spread that load from a column across those 4 piles. Right, another way that we account for larger, deeper foundations was with a caisson. So in this case, we're drilling to a depth. We drill, we want to make sure that we test the soil at the bottom of the caisson. I don't know how they do that, right? Because that caisson could be 40 or 50 feet down, but I'm sure they figured out a way to do that. Make sure the soil is what you want it to be and where you think it is. Put in the reinforcement, fill the hole with concrete. Come on in, you're Jaquan?
Yeah.
Great. Well, join the party here. right? So caissons will be used. They may be used in building construction. Certainly if we're building a high rise, we'd be using caissons. If we're doing bridges or other sorts of things, we'd be using caisson type foundations. You see, in some cases, the bottom of the caisson gets wider at the bottom. That's called the bell. So the bell would be wider to give us more surface area bearing on that soil, right? Because remember, our LBV was pounds per square foot. So if we increase the square feet, either with more caissons or augers, or in this case with a wider bell at the base of the caisson, then that gives us increasing bearing capability. So in this case, we're digging or drilling a hole, putting in formwork and putting concrete in the caisson. A lot of different ways to do this. And again, that's figure 10-10 from the book. Right, so we have a caisson. At the bottom there's suitable soil support material or rock, right? We want to get down to typically to bedrock if we're supporting, and we have a may or may not have a pile cap, and then we have a column that's bearing on that caisson. Oh, another video here. Let me see what this one is. Hold on a second, folks.
It's Aspen Dental's Everyday Smiles event, where new patients get a full examined set of x-rays with no obligation.
Okay, hold on. Let me switch screens here again. Hold on. Stop sharing.
Welcome to this short discussion about floating foundations in Chicago architecture construction and caisson foundations or pile foundations. My name is Jim Janessi. This is part of the first year program at DePaul University. This course is Explore Chicago Architecture through Digital Photography, and this is one of several subjects that we're taking a look at in connection with Chicago architecture. Here is a kind of a cartoonish picture of a small steel frame building. The steel frame is illustrated by these red members, painted steel perhaps being used in construction. And what you see here is a typical way that early steel frame buildings were constructed. The building is held up by a foundation that consists of kind of a raft of maybe steel beams embedded in concrete or even railroad ties and railroad track, as in the auditorium building. And the steel members stretch all the way down to that foundation. The purpose of this foundation is to spread the weight of the building evenly. If these steel members just poked into the ground, they would sink. They don't have much surface area, and they would just sink right into the ground. So the foundation had to be broadened, and finally John Wellborn-Root came up with the idea of having a foundation that was continuous, perhaps even spread out past the edge of the building, so that somehow the entire weight of the building borne by these steel members would be spread. And if the architect were lucky, then the moisture in the ground and the softness of the ground in various areas wouldn't vary too much down here in the dirt. And this building was expected to settle, but it might settle evenly if they were lucky. Now, there is a layer of bedrock underlying Chicago. It's 40 feet down or perhaps further, but there wasn't a very convenient way of reaching it with the technologies available for excavation in the 1880s. So many buildings were constructed this way, and some did. They all settled, and some settled in rather unusual ways. We have here the kind of settling that might have occurred if they were lucky. Notice I'll go back to the earlier slide. Here was the way the building was constructed, and as the weight piled up on top, it eventually might sink a few inches, or in the case of the auditorium building, the foundation walls were so heavy it sunk 29 inches. Now that's really pretty dramatic. However, if they were not very lucky about things, the building might sink something like this, in which case, depending on the amount of uneven settling, things were kind of bad. And you will see some buildings like this. On Michigan Avenue, there's one that's a notable slant to the window. On Wabash, there's also another. And some buildings attempted to correct for this by making cosmetic changes to the way the window frames worked and hoping that the building wouldn't settle any further. Many of the old structures are now taken down because the land became more valuable than the rents that could be earned in such a small leaning structure, and it was eventually demolished. Something better had to be done. Well, let's take a look at a building that had properly settled. Let's suppose it were constructed instead using a caisson foundation or some type of pilings that actually reach down to the bedrock. The bedrock is solid. It's not about to sink unless we have a major earthquake, and then it's all up for grabs. So the bedrock is where tall buildings have to be anchored. The taller they went, the heavier they got, and the less stable they would become if you tried to float them, as this building indicates. So here's what was done. Around 1900, they were experimenting with this. It actually got perfected into the 1920s as buildings reached even higher than 18 stories. This sort of construction adds columns here which are unseen. They've been drilled through the earth, and perhaps they've been spread out where they contact the bedrock. But these are concrete columns that can bear a lot of weight, and in order to strengthen them further, steel cages, reinforced steel, is put into here. So these caissons reach all the way from the level of the earth down to bedrock, and that's actually what the steel members rest on. So whether the earth shifts a bit under this, it has no consequence whatsoever, because the real weight of the building is being borne by the bedrock here. And all the large structures you see in Chicago, anything above 18 stories or so, and frankly, any modern construction, even like the L. When the new platforms were put in at the Fullerton stop, caissons were used all the way down to bedrock to make the L a lot more sturdy than perhaps taking the chance that a floating foundation might sink unevenly in various areas.
Brush your teeth in less than 10 seconds with this
Okay, I thought that one was pretty interesting. Again, if you're familiar with the history of Chicago architecture, right, we used, as he said there, some kind of floating raft foundations, you know, when we started building the city again after the Chicago fire, late 19th and early 20th century. We were using those floating pile foundations or floating raft foundations. And, right, you saw some of the problems that are inherent, right? Either the building settles or the building settles unequally. Again, if you've been to something at the auditorium theater and you walk around in there, it's sometimes a little unnerving because the floor will slope up and down depending on where you are in the building. You may or may not notice it, but it's because of the fact that the auditorium theater, the exterior masonry walls have a lot more weight than some of the interior columns. So in a floating raft foundation, those settle a lot more than the other stuff. Okay, let me get one more video here. Okay, hold on. Yeah, I was we'll have to figure out, I didn't watch this carefully, but I'm seeing that they're attaching something to the sides of the cage of rebar. I'm assuming that's there to guiding or spacers. It was probably, I don't know, 20 or 25 feet worth of rebar, or the steel rebar cage that they. Okay, let me, this is one of the annoyances of Blackboard that I haven't figured a way around yet. If I'm, 30 or 40 slides into a presentation, right? So there's our guy setting the reinforcing cage. Again, another technology is called a steel pile or pile driving. So again, in this case, seems to me more of a brute force method, but we're going to take weight and force and drive a piece of steel into the ground. And I guess I better tee up the next. Right. Let me go to the next slide here and tee it up. Sorry, where'd my cursor go?
If you live anywhere near the I-4 Ultimate construction project, you've probably heard these sounds. It's the sound of pile driving. But what is pile driving for? And is it going to damage nearby property? Concrete, steel, and sheet piles are an essential part of the underground structures needed to create the foundations that support the new road, bridges, and ramps that will become I-4 Ultimate. About 7,000 piles will be driven into the soil along the 21-mile project. There are two types of pile driving, vibratory and impact hammer pile driving. Vibratory pile driving is used when the soil is soft and loose. As the pile vibrates, it gradually pushes the soil down. The vibration made by vibratory pile driving is high frequency and low energy. It's kind of like hitting a boxer's speed bag. If you're hitting it really fast, the impact is relatively low. Impact hammer pile driving, on the other hand, is more like hitting a punching bag like this. High impact and low energy vibrations are emitted from this type of impact. Hammer pile driving is used to make sure the pile is seated in dense soil. All along the I-4 Ultimate Corridor, engineers carefully monitor the levels of vibration in order to mitigate disturbances and to make sure the piles are placed accurately. Of course, you're going to hear it and feel it, but rest assured, we are monitoring to reduce the risk of any structural damage. As an example, it was necessary to drive piles less than 25 feet from this historic property on Colonial Drive at Garland Avenue. During the entire process, no structural damage occurred. And don't worry about the sounds of pile driving keeping you up at night. As part of the construction contract, pile driving is only permitted between the hours of 7 a.m. and 10 p.m. in residential areas. To find out more about pile driving and the entire I-4 Ultimate project, log on to i4ultimate.com.
Okay. Yeah, that's that bang, bang, bang is pile driving, right? If you've probably seen that on a construction project and wasn't quite sure what it was, right? You're basically pounding stuff into the ground.
So they don't remove any of the soil first?
No, for pile driving, it's it's basically brute force, right? In the
Gotcha.
auger catch pile or the caissons, in that case, we are removing soil and then putting something in. In the case of pile driving, we are driving something through the soil. Okay, slab on grade is when we have a concrete slab that's poured directly on the ground. It's obvious it gets reinforced with welded wire fabric or reinforcing steel. We just saw a picture before about a monolithic slab. And in the case of a monolithic slab, the slab and the footing is poured as one continuous unit. It says it uses what are called turn down footings, and you can kind of see where the name turn down footings comes from. This is figure 10-12, right? So you see in this case, the footing and the slab are poured as one unit. Right, here's an example of a slab on grade construction. Again, in this case, the formwork has been set, the rebar is there. In this case, you see this, there's probably some plastic to act as a moisture barrier between the soil and the concrete, right? We're trying to keep soil moisture away from the concrete as much as we can. Right, we do the same thing in a foundation, right? This is on page 179, foundation waterproofing. Right, we're trying to keep some of that moisture in the soil from penetrating the concrete of our building. Okay, one more YouTube here, and we'll take a break.
Whatever the day brings, Grammarly helps you communicate smarter.
Homeowners in luxury San.
Okay, let me find that one here.
Homeowners in luxury San Francisco high-rise are furious this morning over their sinking investment, you could call it. The 58-story Millennium Tower has reportedly sunk 16 inches since its completion back in 2009. It's also, by the way, leaning toward the Pacific. No problem there. Carter Evans is in San Francisco with why this building has moved so much. Carter, good morning.
Good morning. Condos in this famous glass tower range from about $1 million to more than $10 million. But now the building is listing, and that's giving residents a sinking feeling. The Millennium Tower is home to some of San Francisco's rich and famous. Joe Montana once lived here, and Giants outfielder Hunter Pence is among current residents who've recently been told the building is sinking. Jerry and Pat Dotson bought their condo in 2009.
We paid $2.1 million for the apartment.
And you get a great view for it.
Right.
But you're getting closer to the ground every day.
And at this point, the building has sunk 16 inches.
But that's not all. The building is tipping.
It's leaning 15 inches out towards the west from here.
Unlike some other new San Francisco high-rises, the Millennium Tower is not anchored in bedrock.
And you can see that this building has been settled.
Ray Sullivan, a geologist with San Francisco State University, leads tours of the city's sinking and leaning buildings. He says the area where the Millennium Tower is built used to be in the water. After the gold rush, parts of the bay were filled in to create more land.
Bedrock is 200 or 300 feet below us, a long way down. There's a lot of mud, lots of sand on top, and I would be concerned if we have a major earthquake.
Not a problem, according to Millennium Partners, who said in a statement, the building was designed and constructed to the extraordinarily high standards established by the city and county of San Francisco for this type of structure. Instead, the developer blames a new transit center across the street for destabilizing its luxury tower. There's a lot of finger pointing going on right now. But the one fact remains, if they had drilled pilings down to bedrock, would we be here?
No, that is the heart of the problem.
And until there's a solution to stop the sinking, many who live here may be stuck here, unable to sell.
This is the major part of their assets. And that's for a lot of people is a very terrifying thought when they think about the Millennium not going forward and fixing the building.
The Homeowners Association is exploring all of its legal options right now, including pursuing damages from the builder, the developer, and even that transit center. Gail, the developers thought that building would settle about 6 inches over its lifetime, not 16.
Right, that's a big difference. Thank you very much, Carter.
Hi, Rex Moore with the Motley Fool.
Yeah, generally speaking, in the world of construction, when the contractors go away and the lawyers show up, it's generally a bad thing. So, again, in this case, I'm sure a lot of lawyers will get very rich in that situation, and someone in the tier of contractors is going to get their backside suit off, right? The developer, or the structural engineer, or somebody else. So, like in a lot of things, the lawyers make money and everyone else loses. Okay. Any questions on Unit 10?
I just have a quick question. So slab on grade, are there no basements?
Sorry, Nicole, I pushed the wrong button. You had a question?
Oh, no problem. That was Ayana. Just
Sorry.
making sure slab on grade equals no basements, right?
Yes, that is correct.
Okay, I'm just making sure that I'm imagining all this stuff in the right order. Okay.
Yeah. I mean, we in a building with a basement, we've poured the footings, we've then pour the foundation walls, and then typically we pour the slab as the last thing. And again, there'll be some kind of expansion joint between the slab and the footing. In the case of that monolithic slab, it's slab and footing together, so there would be no basement. Any other questions? Okay, why don't we take maybe a 10-minute break or so, and we're going to go right to activity 10-1, which is back to the Sullivan residence. So maybe while you are getting up and stretching, you can dig out the sheets that they talk about for the Sullivan residence, and we'll break into groups and spend a little time with Sullivan, and then come back and answer questions. So we'll see you back here at, let's say, 5 after the hour. Yes, Christoph.
I actually had a question about the video you just showed us. So they said that the bedrock would be 200 to 300 feet below the ground level. So what exactly did they do to establish a firm, a secure foundation for the building if they didn't go down to the bedrock?
I assume they used some variation on that floating raft that we saw in the video from Chicagoland, right? Floating raft was how we, again, in the late 19th and first part of the 20th century, how we built buildings here. So I'm assuming that they did some variation of that floating raft. And why this particular, I don't know enough about San Francisco architecture to know if, what's common practice. Certainly drilling a caisson or a piling down 200 feet is going to be a challenge, but I'm assuming someone has figured it out. But that that particular building has seemed to have made the news, right? Because a lot of rich people are having stuff slide across their floor.
Do you happen to know if there's a documented case of the farthest drilling or the longest use of caisson?
I do not. I do not. That's a good question. I don't know the answer. I wasn't aware that until I watched that video. I wasn't aware that bedrock was so far down in that area. So I don't know what they do there. That would be. Again, I know they in the video here, they said bedrock in Chicagoland is what, 40 or 50 feet down. So that seems more reasonable to be able to drill or auger or drive a piling down 40 or 50 feet. 200 feet is another matter.
Is it impossible to go that far?
I don't know. I don't know whether it's possible. I mean, I don't know that much about how buildings in San Francisco are built, right? I mean, they obviously have to contend with earthquakes, which we don't have here. And Tokyo would be another city that's earthquake prone. I think the Japanese have figured out how to build resiliency into their buildings such that they're not damaged by earthquakes. The other city that you don't necessarily think of as having seismic issues is St. Louis, right? St. Louis is a city that's fairly close to the New Madrid Fault, where there was a major earthquake in, I don't know, it was 1803 or 1805 or something like that, right? Long before St. Louis was much of a city, but if there was ever a big earthquake on the New Madrid Fault again, I don't know what would happen in St. Louis. But since I don't know that terribly much about seismic considerations, because it's not something that we necessarily have to worry about here in Chicagoland. "72-meter high caisson," right? So that would be 272 meters is almost 300 feet. Okay, good question. I don't know that's one I don't know the answer to, but let's give me a minute to get a break here and get set up, and we'll get back in 5 or 6 minutes.